Hello friends, I am Dr. Nitin Naik, Department of Structural Engineering, Sanjani College of Engineering, Kopargaon. So friends, we have already discussed about the fundamentals of theory of elasticity and plasticity. Now let us move further for a new topic which is related to stresses again. So let us take a rapid recap. We have already discussed about stress at a point. So stress at a point can be completely defined by its 9 components. We have already discussed how the 9 components can be obtained through resolution. So 9 components acting on 3 mutually perpendicular planes. So we are having this figure, and this is x-axis, this is y-axis, and this is z-axis. And this plane, please follow the cursor, this plane is called as x plane because if you draw normal to this plane it will be parallel to x-axis. Similarly, this plane is called as z plane because if you draw normal to this plane it will be parallel to z-axis, and hence this is y plane. Similarly, this is also a x plane. Okay, this is also one more y plane bottom side, and to the rear side this is z plane. Okay, so these are the different planes. On x plane 3 components are acting: sigma x, tau xy, and tau xz. We have already discussed significance of these uh, letters suffix. Tau xy means stress is acting on x plane in y direction. Tau xz means stress is acting on x plane in z direction. So here these are this row, it shows plane on which the stresses are acting, while this column it shows the direction in which the stresses are acting, and this is called as stress at a point. This is stress matrix. Now let us discuss the variation of stresses. Here we are having again the x-axis, y-axis, and z-axis, and this is origin of the reference system. And there are different planes. First x plane, this is again a x plane, y plane, this is y plane, and here this is the front z plane, and this is the rear z plane. So there are 6 planes. Now let us consider x plane. This is x plane. To the left of the this cube, x plane. On this plane the stresses acting are sigma x, please follow the cursor, tau xy downward, tau xz. Okay, now when we move, the size of this paralleloiped is, this is dx, this is equal to dy, and this is equal to dz. When we move towards the positive x plane, we will call it as negative x plane, or say left side x plane. When we move through distance dx, we will reach to second x plane. This is the x plane. Now on this plane the stresses acting are sigma x. Remember, here also this is sigma x. But when we move through distance dx and we reach to this x plane, the stresses, now sigma x changes to gamma sigma x by gamma x into dx. So this is change in the stress. Similarly, there is change in tau xy. This is tau xy. On this plane the stress is tau dash xy, means these two stresses, this tau xy dash and this tau xy, they are not having same magnitude. So there is a change in stresses. Now here this is sigma y. Let us consider the bottom y plane. This is sigma y, and when we move through dy, we will have a stress on the second y plane as sigma y plus dabba sigma y by dabba y into dy. And same is the case with stress sigma z. This is sigma z and it changes to sigma z plus that increment. Okay. Now the changes in the stresses are because the right face is at a distance dx from the left face. Now let us shift the origin of the system to the center of gravity of the element. Why we are doing this? To simplify our problem. Previously this was the origin. Now I am shifting the origin to the CG of the element, CG of the element. Now the advantage of shifting the entire system of axis or the origin to CG is that when we shift the origin to the new position, that is CG of the element, and if we take moment of stresses about the axis, we can eliminate the normal stresses sigma x, then sigma y, as well as sigma z. We will see how it is beneficial for us to shift the origin to the CG. Before that, let us discuss or let us consider the Z plane. Now I am considering the Z plane. Please follow the cursor. This is the Z plane. This is the Z plane. Why this is Z plane? Because if you draw normal to this plane, it will be parallel to Z axis. Now we have shifted the origin to the CG of the element, and now this is the Z axis. This is the Z axis. In this figure, this is the Z axis. And this side is equal to dy, this side is equal to dx. Okay, and thus we can take moment about this Z axis, moment of stresses about Z axis. Now since I will go back, if you take moment of this sigma z about Z axis in this system, it will be 0, because now the Z axis is along sigma z, x axis is along sigma x, y axis is along sigma y. So there will be no moment of these stresses about the respective axis. Means there will be no moment of sigma x about x axis, there will be no moment of sigma y about y axis, there will be no moment of sigma z about z axis, and thus we can eliminate those stresses. The moments will be only because of the shear stresses. Now this is dy. On this dy, means on this plane, tau xy is acting, so only stress of tau xy will be there. Sorry, moment of tau xy will be there about z axis. Let us move to the next figure. Now if we consider the x plane, this is x plane. Please follow the cursor for better understanding. This x plane is having dimension dy and dz, dy and dz, and these are the shear stresses acting on it. These are the shear stresses acting on it, and this is x axis, because now the CG is origin of the system. Okay. Similarly, let us consider the y plane. This is y plane. It is shown in the figure, y plane. Okay, and this is y axis, and dimensions are dx and dz. Okay, now if you take moment about this y plane, sorry, y axis, then there will be moment of the shear stresses only. These blue color arrows, they are showing the shear stresses. Green color arrows, they are also showing the shear stresses. And in this way, shifting the origin to the CG of the element will eliminate the effect of normal stresses. Only shear stresses will be there. Now with reference to that, let us discuss one question. about equity of cross shears. Tau xy and xy, tau xy and tau yx. These are the two stresses. Okay, slight difference is there. Tau xy is acting on x plane in y direction. Tau yx is acting on y plane in x direction. Let us see what will be the result. Okay, our question is prove that the shear stresses are complementary. Now consider an infinitesimal rectangular parallelepiped surrounding point P. Okay, so this origin is point P. Let the dimensions of the sides be dx, dy and dz. We have already discussed it, dx, dy and dz. The reference axis x, y and z are passing through the centroid of the faces or CG of the element. This is face, x plane, and the x axis is passing through centroid of this face. CG, this term is applicable for solids. Centroid is applicable for a plane. Okay. Now, shear stresses on left x face. Please follow the cursor. This is left x face. Shear stresses acting on left x face. Tau xy. This is tau xy. Shear stress on right face is tau xy. Previously it was denoted by tau xy dash. Tau xy dash is equal to tau xy, this stress, plus increment in the stress, dabba tau xy by dabba x into dx. Similarly, the stress acting on bottom y face. So this is bottom y face. First stress is tau yx. Now we will move through dy and we will reach to the top y face. And on top y face, the stress acting is tau yx, means this stress, plus the increment. Next. Now, let us take moment about z-axis. Here we will use the right hand screw rule. This is right hand screw rule. This thumb, it points towards the direction of axis, and this curved figure shows the direction of positive moment about z-axis. We have already studied it at school level. So we will take moment about z-axis. This is z-axis, remember. So this is the z face. This is the z face and this is z-axis. Now we will take moment about z-axis. If we observe the z face from this direction, okay, I will draw one arrow. Now we are observing the z face from this direction and this is the view. This side is equal to dy, and the bottom side is equal to dx. Okay. Now the stresses acting are along this face. Tau xy is acting. Tau xy. So this is tau xy. Means this stress, this arrow, this is tau xy. And on the opposite face, the stress acting is tau xy plus the increment. Tau xy plus the increment. Previously we have denoted it as tau xy dash is equal to tau xy plus the increment. Similarly, on the bottom face, means on this edge dx, the stress acting is tau yx. So this is tau yx. This is tau yx. And on this edge, the stress acting is tau yx plus the increment. So let us take moment about z. So this is the z-axis. Okay, now let us take moment about z-axis. So first stress is tau xy. Now stress we can convert it into a force by multiplying it by the area on which stress is acting. So stress tau xy into area on which it is acting. So this tau xy is acting. Now I will erase all other details for better understanding. Yes, okay. Now let us take moment of tau xy. So this is tau xy. Now I am taking moment of this tau xy. Here this is tau xy. I am taking moment about z axis. This is the point, z axis. Okay. So the stress tau xy. This tau xy stress is acting on this area. Please follow the cursor for better understanding. Dy into dz, into dz on this plane tau xy is acting, hence dy into dz, area into stress, force, and we are taking moment about z axis. So z axis is located at a distance of dx by 2 from this space, hence into distance, this is moment, force into distance, this is complete force, and this is distance dx by 2. Okay, plus let us take moment of this force about z axis. So force is the stress with increment into area dy by dz into distance of this stress from z axis, this is dx by 2, this is dx by 2, and this is the direction of moment, anti-clockwise, this is also anti-clockwise. Okay, the curled fingers are in anti-clockwise direction, so positive again. Okay, so this is the moment. Now moment of tau yx about z axis, moment of tau yx about z axis. So tau yx is acting on this y plane, this is tau yx. Now we are taking moment about z axis, and the distance of tau yx from z axis is dy by 2, dy by 2. So see the force. Now this is clockwise direction about z axis moment. So the moment is stress into area. Stress is tau yx, and the area on which this stress is acting is dz by dx, dz by dx. So dx into dz, area, into distance dy by 2. Similarly, the moment of this stress about z axis is stress into the area on which it is acting. So stress into dx by dz into the distance. This is the distance dy by 2 must be equal to 0 for equilibrium. Now let us divide the above equation by dx into dy into dz. To simplify this equation, what we will do, we will divide the entire equation by dx into dy into dz. Now see what will happen. If we divide this above equation by dx into dy into dz, and now dx, dy, dz, these terms will disappear, and there will be tau xy upon 2. In the second equation, tau xy upon 2 will be there, while dx into dy into dz will disappear, plus dabba tau xy by dabba x into dx will be there, minus, now in this term dx, dy, dz will get cancelled, tau yx upon 2 will be there. In the second term, tau yx upon 2 will be there, minus tau yx upon dy into dy by 2 will be there. Now, since delta by x is very small, dx is also very small, dx is also very small. So let us ignore the small terms. Now which terms we will ignore from this equation? We will ignore this term. Okay, again we will ignore this term. So now we are having tau xy by 2 plus tau xy by 2 is equal to tau xy. Tau yx by 2 minus tau yx by 2 both are having minus sign. Hence we are having tau yx right hand side is equal to 0, and thus tau xy is equal to tau yx, right? And here this is called as the complementary stresses. Similarly, we can derive tau xz is equal to tau zx and tau yz is equal to tau zy. Remember, when you take moment about z axis, you will get relationship between tau xy and tau yx, tau xy and tau yx. When you take moment about y axis, you will be having relationship between xz and zx. When you take moment about x axis, you will be having relationship between yz and zy. Now, while solving question in examination, you have to take moment about x-axis, y-axis and about z-axis. So, you have to solve the complete derivation. You should not write simply taking moment about z-axis and hence we can write like this. No, you should completely derive these equations or this relationship. So, it shows that the shear stresses are complementary. See, our question was prove that the shear stresses are complementary. So you can prove like this, the shear stresses are complementary. Okay, and thus to completely define the state of stress at a point, 6 independent components instead of 9 are required. What we have studied in the first slide, we need 9 components. These 9 components are there. Now these 9 components are reduced to 6 components, namely sigma x, sigma y, sigma z, tau xy, tau xz and tau yz. There is no tau yx, no tau zx and no tau zy because of the relationship. Because of this relationship, now only 6 components are there, and hence the stress at a point can be expressed with the help of these 6 stress components. Again, the row, it shows the plane on which the stresses are acting. So these stresses are acting on x plane, these stresses are acting on y plane, these stresses are acting on z plane, while the columns shows the direction in which stresses are acting, like this: x, y and z. So in this way, stress at a point can be defined with the help of 6 stress components. The question may be like this: how stress at a point can be defined with the help of 6 components? Again the same derivation you have to perform.